It is my pleasure to introduce our speakers for today's tutorial, Amy Elliott from Oak Ridge National Laboratory and Emma White from Ames Laboratory. Amy, Emma, take it away.
Thank you, Diane. My name is Emma White, and I work at the U.S. Department of Energy's Ames Laboratory and Iowa State University. I have been in the powder metallurgy field for 10 years now and focus on high pressure gas atomization powder production, including various applications of those powders, such as permanent magnets, nickel-based superalloys, as well as additive manufacturing of a lot of different alloys, and then also some nanopowder work for battery materials.
And I'm Amy Elliott. I work at Oak Ridge National Lab. I work in powder-based additive manufacturing systems, have background in particle-loaded inkjet fluids for additive manufacturing, and we work in general on ceramic and metal sintering and infiltration of additive manufacturing parts. I have about 10 years experience in additive manufacturing and about 5 years experience developing safety procedures and standards for our powdered metals at ORNL in the binder jet field. We'd like to acknowledge Matt Osborne from Global Advanced Metals, who helped develop this course originally. So this workshop was organized because there are powders used in lots of applications and industries. And there are many new users of powders as we see more and more additive manufacturing out there. Powders are a unique material. They don't act like plates, slabs, or other monolithic forms. So there are unique challenges with that. So how do we stay safe? And how do we maintain the quality? And how do we do that economically? So as we go through this, feel free to take notes on your questions. We'll have Q&A sessions as we go along. So whether you're a user, a scientist, an industrial person, someone who is in manufacturing, you do need to get to know powders and their safety and quality, because you can't just leave it up to your safety personnel. Their knowledge is broad, and they're not going to necessarily have the depth that is needed to keep things safe. So you'll need to help them out. The users will have the most powder contact, so that's your technicians. So they need to be safety minded too. And if you are developing requirements, you can really go too big or too small. So we need to find the middle ground. So if you have too little requirements, you're going to create danger. And if you have too many requirements, you're going to be inefficient and you're going to have unneeded costs. So at the crux of this problem is the size of the powder. So powders are small, obviously, and because of their size, they have high mobility. That means they travel easily. They get into nooks and crannies. They can become trapped. They can become suspended in air, and they can loft and stay there. As they're suspended in air, as they travel easily, they can be ingested through the mouth. They can be inhaled. That's a big problem that we'll talk about, is how respirable they can be, and then what that can do to your lungs. Another reason that powders are dangerous is because they're really reactive. Because they're so small, they have a lot of surface area, so that gives them a lot of potential for being reactive, exploding, burning. So there's chemical reactions that can happen with powders. Just some examples: fireworks are obviously metal powders, and rocket engines, solid rocket boosters, are made from metal powders. So just to give you an idea of the different sizes that we're talking about, so I think we're all familiar with the size of viruses nowadays, but this is that size range from here in microns. We have cornstarch here, copier toner, and these are our press and sinter powders. And then this is usually our respirable range. Just some case studies. I think I skipped one. Okay, here we go. So kind of some case studies about how powder explosions and powder safety has been an issue. So these mills that are producing flour, this is actually a historical event where the Washburn mill exploded because of some powder that got flocculated and then sparked. So this is actually goes back way back when. And then on the breathing side, silicosis is a big cause of death in mining. So there's a lot of restrictions around silica and powdered silica, which we'll talk about. And here's just a modern example of an explosion in a factory in China where they were dealing with metal polishing dust, and that ignited and did kill several people. So it's killed 68 people. So powder safety is very important. It's not something to be pushed to the side. Here in the US, this was a case where a 3D printing company, actually, and that's what we'll be focusing on today, the 3D printing company was cited for many violations of workplace safety. And this is a big reason for our workshop today. There's a lot of, like I said, there's a lot of people getting into metal additive manufacturing that don't necessarily have a background in metal powders. And so this is to kind of get you, get a broad overview of the type of things and standards that you should know about, and that there are actually a lot of these standards that you should know about. So that's the same example. So we want everyone to come home at the end of the day the way they went to work. So that is, a big reason why, the main reason why we want to focus on powder safety. But another reason, obviously, is the bottom line. These types of accidents are obviously very costly, and so that's another reason. And so with that, I will hand it over to Emma to talk about powder quality.
So powder quality is also important and something that we don't want to ignore, but again is secondary to the safety of those people that are operating and working with the powders. But quality is important because your input really equals your output. If you have low quality powder going in, you're going to get low quality materials or products out. If you have a poor you have poor control of the environment that you're working with, sorry for my dog, that will give you a low quality output too. Powder can be recycled, but there are rules towards being able to reuse the powder. You need to minimize contamination, so something that's already gotten out and dispersed on the floor and then collected again is harder to recycle. And also that it can include powders that have just been exposed to moisture or air. Some of those can react or absorb the moisture and agglomerate and cause issues there. So you need to be cognizant of what your powders are being exposed to, and that even the best system and the best organization and the best process quality that you have will allow some contamination to happen as you use those powders. So you just need to be aware and monitoring that and controlling it. So this is an example of a way that 3D printing has moved forward and been able to be applied with the Cessna engine, being able to work on building entire parts out of 3D printing by controlling that quality. And you can go to the next slide. Again, you need to control quality in the medical industry. Again, this part will be in a patient for a long time, so you need to make sure up front that those pieces aren't going to have defects in them that would require costly surgery and probably liability there, and replacement of those parts over time to make sure that those are in control. Another area that would be important for looking at your quality is the thermal barrier coatings in engines and making sure that those are more efficient by being able to operate at higher temperatures with those coatings on them. And, you know, again, that would be an important quality metric by making sure that coating is not contaminated and it's adherent and uniform, because a failure of a jet engine would again be very costly and expensive for not just the company itself, but then also potentially having downtime for mitigating that issue in any other engines. And then again, could be a safety issue with that failure of that engine. Just kind of a fun aside, you know, it's not just the metal powder industry that's looking at quality of powders. It's just even the food industry and looking at, for example, cocoa and making sure that your cocoa is uniformly dispersed with its sugar and milk and cocoa powder, and all of that stays mixed together appropriately in order to give you a high quality drink at the end of a cold day. Powder processing, again, is not new. It's something, as Amy showed, that's been around for a long time and is even continuing to move forward into new areas and areas that haven't traditionally been powder metallurgy areas, such as recyclable metal fuels. So powders can, like we talked about, solid rocket boosters can be used as fuels. And so those can be, are looking at developing those into new fuel sources. So next, we'll move into just an overview of powders from start to finish. And I'll be talking through those topics just to give everyone kind of a same starting point to work from, just in case some of us are new to the powder industry.
I shared the screen with you, Emma. Were you able to?
There we go. Can everyone see that all right?
Yep.
All right, so moving through, we're going to talk about production of powders, sorting and sizing of them, handling and storage, and then the applications and how those feed back to each other. So as far as production methods of powders, and I'm going to try and go through these topics fairly quickly and at a high level, as most of the attendees are probably fairly familiar with this area. There are mechanical methods of producing powders, including crushing and grinding and milling to produce those powders. There are chemical methods such as reaction pathways, sol gel methods, or precipitation of ions from a fluid onto a substrate, or through electrolysis. There's also melt methods of powder production, such as gas atomization, water atomization, plasma atomization, rotating disk atomization, and electrode induction. Melting with atomization capability. So the method that you use to produce your powder is going to have a significant effect on the powder that is produced. So this is an example of how the method that is used to make the same MARM 246 powder, and this is data back from about the 1980s, but is still relevant today as most powder producers are using fairly similar processing methods and approaches as what they used back in the 1980s, as those are the methods that have been certified, and those are the equipment that they still have and are still using. And so those are the ones that they're still utilizing technology-wise. So this shows a rapid spinning cup process and then a rapid solidification rate process, which are both based on that rotating disk atomization, where the melt is flown off the edge of a disc that's rotating, and those fine filaments break up into droplets. There's vacuum soluble gas atomization, which is now augmented with a gas atomizer. There's the prep process, which uses a plasma torch on an electrode that's rotating to break up the material, and then the gas is used to atomize those into fine droplets. And then there's also gas atomization listed on here with a free fall gas dye. So not only you can see just the difference in size distribution. This is weight percent versus particle diameter. So your particle diameter is shifting significantly based on the process that you're using, but also your cost is changing. Prep is commonly known as the most expensive method to make powder, but it makes the really, really high quality powder. But then some of these other methods, such as free fall gas atomization, are a little bit maybe cheaper. But if you're using inert gas, that becomes more expensive than if you're using a water atomized process. So you can see there, if you're using gas atomized powders, you're getting really nice uniform spherical powders. However, using water to atomize and break up that melt stream, you get kind of oblong off spherical shapes that are a little more jagged and non-uniform, which could have effect on how you're able to process those. And then again, looking at your atomization for your AM process feedstocks, those ranges are highlighted there for the 15 to 45 for laser melted powder bed fusion, and generally kind of the 45 to 106 micron size range for electron beam melted powder bed fusion. And if you're just looking at the gas atomization process, that's only about a 15 to 20% yield. So, you know, that moves into your cost range there too, and providing a higher cost because you're only able to use about 20% for your specific process, and then the rest of that has to be stored as inventory. So all of these factors kind of need to be taken into account in terms of both safety and quality, because your production method is going to affect all of those pieces, and in the end, your cost point as well. When you're taking your powders and then sorting and sizing them to use only the powders that you want to use for your process, there are a number of different methods. You can use a standard screen or a sieve to process the powder as it goes through a grid of metal, or there are plastic grids too, to cut the size fraction at only the sizes that you want. And then there's also air classification methods, which is more traditionally used, kind of shown there in A and C, where your powders are injected into a cylindrical vortex where the powders can come out at different sizes based upon how you set your gas parameters and how your chamber is configured. And the air classification is typically more expensive than your standard screening sieving. That's your kind of cheapest method for classifying your powders. And then the air would be used for more on the under 20 micron size powders. You can also use elutriation or settling of the powders, and that's shown down in the bottom center, where by moving air through the powder bed, you can kind of size classify the largers to the bottom, and the fines will settle toward the top as you kind of loft the powders there. And then even just vacuuming your powders can help you sort and size them. Another settling method that I've used for nanoparticles is centrifugation, and that's shown on the right here, where you're using a centrifuge to pull down powders that are dispersed in a fluid. And actually the time that you're centrifuging and the speed that you're centrifuging at, you can change those, and those will cause you to get a different size powder that's pulled out of the fluid. So you can monitor and select different size fractions by monitoring your centrifuge parameters. So these are some of the kind of top level sorting and sizing. Again, screening and sieving is been around for a long time, and it is correlated back to the aggregate and construction industry. But when we're looking at metal powder specifically, the ASTM B214-16 is the method that you want to follow, and this is just the high level of the test sieves that you can use, as well as what those sieve numbers and particle sizes correlate to. So a lot of times when you're getting a powder or ordering a powder or producing a powder, these are the certifications that you're going to use when advertising that powder or kind of certifying that powder. For handling and storing these powders, it's very composition dependent on how you need to go about it. With packaging, you need to make sure that your powder is non-reactive with your packaging, obviously. However, there's also other considerations such as electrostatic discharge. So if your material may be more prone to kind of sticking to the side of your container, you may need to change your containers. Nickel powders sometimes have that issue. Also, your atmosphere that you're handling or storing your powders in is quite critical. For some materials such as aluminum that are more sensitive to moisture content, you might want to be only processing those powders in a glove box or a dry box in order to be able to maintain the quality of that powder and make sure that you're not getting absorbed moisture on the surfaces of those powders, which would cause them to agglomerate or cause them to react and have a different oxide surface, which would then kind of degrade your process again. When you're shipping those powders, again, there's a specific DOT regulations for flammable solids that metal powders fall under, and you need to be careful and make sure your SDS or MSDS is corresponding to those, and that you've included all the proper information for the receiver, and that your container, again, is non-reactive, and potentially a lot of the powders that we see are sealed under an argon atmosphere or some other inert atmosphere to make sure that there's no oxygen, again, present in that shipping container that those particles could potentially react with, even if they're fairly non-reactive powders. When you're shipping, those powders are also going to be jostled around, and those powders then will size segregate within the container based on the motion of that container. And so you need to be careful when you get that powder to make sure that you don't just use the top of that container or the bottom of that container or just pour it out. You need to remix that container before you use it, because that will affect your size distribution, and then affect the quality of your build or your consolidation method. And another factor that we recently became aware of at Ames is just even aging of your powders. Some compositions of alloys will just age at room temperature, and so as you're shipping those or as you're storing those, you need to be aware of those compositions that will change with just time at room temperature and under ambient conditions. And so making sure that you're aware of those factors is really important for the particular powders that you're dealing with. So just kind of a summary here on the powder handling effects on quality. We want to make sure that you're handling carefully, because your quality will be affected by how you're producing and then handling and storing and shipping those powders. You're going to get contamination on the surface of those powders, whether that's additional reaction of the oxygen or carbon contamination on the surface, since carbon is just prevalent everywhere, or whether you're potentially getting other materials mixed in during your process and increasing the amount of impurities on those surfaces. On the right here, there's an example where an aluminum build was affected by contamination from a nickel-based superalloy powder. And this happened just because of a new employee wasn't properly trained and aware of the issues with powder handling, and they were unable to get good builds in this plant because there were nickel-based superalloy powders that were coalescing within the build and causing these crack features. And so that's just one example that it was just an awareness issue and a new employee that wasn't fully trained. And once they were able to diagnose that and analyze the problem and really be aware just upfront in the issues with powder handling, as a challenge for any company, it's really something that you need to be careful as part of the project workflows. So you must be careful and make sure that everyone that's involved in the process has their proper training and awareness of the dangers among all of your staff. And again, it's just far better and easier to solve a problem up front than to have to solve a problem like this aluminum alloy build afterwards. And then again, your powder handling is going to have an effect on your consolidation, whether that's during shipping, your jostling of your container caused your size segregation to occur in the container, and those size effects, then you're using the finer powder pulled out on the top from the beginning, and then you're getting a different powder flowability or different density in your part or different packing from your different size distribution, could have a lot of issues downstream. So those are things that you need to be aware of. And just on a high level, you know, the powder metallurgy field is so broad and includes so many different areas that each of these areas are going to have different considerations for handling and quality. And maybe, you know, the area that you're in can learn from another area, or maybe your area is less complicated than another. So, you know, different factors are going to be important for different people or in different industries, such as, you know, dry pressing versus slurry casting versus coatings and composite materials versus metal injection molding versus additive manufacturing. Just for example, you know, if you're making a metal matrix composite, you're mixing together base metal powders, lubricants, and alloying elements. So there you need to be a lot more careful with the mixing versus maybe your metal injection molding is a really narrow, fine size distribution. So your mixing isn't as important, but your handling is more important there because your fine powders are going to be more of a safety consideration. So all of these pieces need to be taken into account, and you need to be aware of those processes throughout your entire workflow. So with that, it's my last slide there. I will hand it back over to Amy.
All right, thank you, Emma. Okay, so now we're going to talk about sources of quality reduction, specifically in additive manufacturing. Specifically, we're going to talk about electron beam melting. We're just going to call it E-beam, and then laser melting. So we'll just call that laser. So you probably know how these work. We'll step through them, those that might not know. But just in general, powder quality is the #1 factor that's going to affect the quality of your printed part, and as Emma has mentioned, and there's also a lot of literature coming out about this. And at ORNL, we actually did a study that showed directly linked the porosity of the final printed parts to the atomization process that was used to make the powder. And just as a hint, the more expensive the process, the less porosity was in the powder. So that just really showed us it doesn't really matter how fancy or complex your laser powder bed or your electron beam powder bed system is. If you have low quality powder, you're going to have a low quality part. So the second reason to talk about this is that with additive being a new field, there are unique things about those processes that affect powder quality as you cycle the powder, and you're not going to see these in any other processes. So mainly what we're talking about is this high temperature thermal cycling. So before we get into that, let's talk about how these processes work. First, electron beam and laser are loose terms that we use in additive manufacturing, but technically they're called powder bed fusion because we're building the parts layer by layer in a powder bed, and that powder is being fused by the laser electron beam. So we spread a layer of powder, we use the laser electron beam to melt that powder selectively. We drop the build, spread more powder, and then we repeat. The electron beam works like an old CRT tube TV. The electrons get pulled down using a differential charge, and their trajectory is guided by a magnet. So it's really fast. Because we're using electrons, though, we have to do this process in a vacuum. And that's going to come into play into our powder quality, which we'll get to. The laser powder bed fusion, or just laser, works by aiming a laser into a set of mirrors, which draws the laser onto the powder bed. And it is a lot slower than electron beam, but it has advantages too. We didn't include much discussion on binder jetting. If you're interested in that, I'm happy to go into more detail or ask your questions. It's actually my main area of expertise. But most of our discussion is around powder quality in these powder bed fusion processes because it's that intense thermal cycling that is the main issue. So now that you know the differences between the two main metal AM processes, we'll talk about the sources of quality reduction. So as you're building a part in the powder bed, you have the printed part and you have the surrounding powder. In electron beam, that surrounding powder actually gets partially centered with each layer, and that helps the print properties, but that does change your powder. So when you recycle that powder, you're going to see a quality change due to that partial sintering. So these are the things that are going to change while you're thermally cycling. Your fines are going to go away, which is those fines are part of that nice bell curve that you want with your particle size distribution. They can either melt into larger agglomerates or just stick to a nearby larger particle, like is happening in this image. And then the second way your powder quality is affected is by the chemistry changes from thermal cycling. We all know that as elements are heated, they are more reactive and basically they move around more easily. So in powder bed fusion, electron beam or laser, the powder gets heated anywhere from 400 degrees Celsius to 1,000, depending on what material you're building with. And that's not the melted part, that's the powder bed. And so there will be chemistry going on between the powder and the environment. So elements like oxygen can creep into the powder. We all know that metals don't want to be metal, they want to be oxides. So those are the major things happening in the powder bed fusion processes that you're really not going to go see. You're not going to see this in a typical powder metal process because you're not repeatedly thermally cycling your powder bed that you're using for the next build. There is actually a new electron beam system on the street that doesn't sinter the powder just for this reason. So that's kind of the progression of the technologies. They're getting away from that sintering. So contamination. So this is a little bit a topic on its own. So quality reduction is obviously caused by contamination too. So when we talk about contamination, we're saying the addition of foreign materials or elements into the powder. So that's by overlaps with the thermal cycling discussion. And then also we can talk about the actual physical powders entering that are not supposed to be there. So Emma gave an example about how some super alloys were present in a print that weren't supposed to be there, and that created some major defects. So we'll talk about those sources of contamination. So getting back to thermal cycling and diving in closer. So I'm thinking most people knows what happens to certain metals when they're melted in a vacuum, right? They vaporize. And one of the metals that is particularly susceptible to vaporization is chromium. So we know that some elements have low vapor pressures like chromium, and they can leach out at those high temperatures in a vacuum chamber like we have with the electron beam. So your stainless steels, your Inconels, and lots of alloys have chromium in them. And so that vacuum is not only an issue for your part chemistry, because you will see a change in that, but it's also the powder, it's what that powder leaves behind in the machine. So these materials do get deposited on the chamber walls, and that can be a source of contamination as well if you change your powder out. So on our electron beam systems, whenever we are changing a feedstock, we actually take any piece of hardware out that we can, and it gets feed blasted to remove that layer of metallization. And then we actually grind down the chamber walls to remove that layer as well. So anything that can't get removed, it gets ground down. So the vacuum is an issue, the high temperature in general is an issue, and combining those, like we have the electron beam process, makes it kind of a compounding problem. So getting back to some issues with E-beam, here's just a study on powder quality that was done a few years back. They performed multiple builds with the same powder, and then they analyzed the powder after each build. So this study was being done with Ti-64, which is a popular titanium alloy. And so what they found in the study is that their oxygen did increase from their 0 to 21 uses. Their aluminum and vanadium content was stable, and they did see a narrowing of their particle size distribution. So not only did those fines go away, but they did see a little bit of reduction in their larger powders. Their flowability did improve, and they think that that was likely due to removing moisture over time, but it could also be due to removing those fines. And then they did see changes in properties and actually an increase in yield and ultimate strengths due to the extra oxygen. Ultimately, in this study, they concluded that recycling this powder was okay for Ti-64. Here's a study that was done at Oak Ridge to show the effects of powder recycling on Inconel 718. So they made the same build 6 times, and they did elemental analysis to see how the chemistry changed. So they made a nice plot of the major elements and how they change over time. And they found also that the flowability increased, and they did find that the elements stayed within spec. So this is good news. This means these powders are recyclable, but they determined that, you know, they actually did start with some really nice powder, and that might be a reason why they had such good results. So that's just something to keep in mind. Like we said before, the powder that you start with is a big factor. So another source of contamination besides the process itself is material swapping. So that's when you're actually changing the type of material you're using. So example, going from a steel to a nickel alloy. So it involves removing all the powder from the system, cleaning everything, hopper coater, build chamber overflow sieve system. And for us, it usually takes one person several days, usually a whole working week, to swap the material on the machine when done properly. And this is why most companies avoid this if they can. They will buy a machine for a specific material and never change that material because it is such an involved process. So just typical cleaning procedure is you really just have to disassemble anything that the powder flows through or touches. You have to empty those components as best you can, tapping and rotating, vacuum them out. And then we wash and scrub with soapy water, we rinse, and then we use small amounts of alcohol to let it dry. So that's just our general procedure. So getting into the weeds on how to properly clean, this isn't a standard or anything, but this is how we do it. So it's something to build off of in your own lab space. But just as an overview, there's just a lot of different components to clean. So first off, in this laser system, you can see that there's a sieve station where the powder gets processed that has to be cleaned. Here is the inside cabinet on the top right, and that's where we can access the powder overflow, the airflow that where you're trying to capture the soot that comes off of the laser process. There's an air filter that needs to be changed out. For the electron beam process, there's a lot of shielding that may or may not get reused for a different material. And then there's the recoater mechanism. There's just a lot of different pieces. So drilling down into the inside cabinet of this 3D printer, this laser powder bed system. So from the top, this manifold is actually what the air knife is getting pumped into. So that soot is getting pulled into this vent and then through this air filter. This is not typically a source of contamination, but there is a safety issue associated with that we'll talk about. And then as the powder gets pulled over the build area, it gets the excess powder gets swept into the overflow. So you can see the overflow canister and the overflow hose. All that powder is intended to be recycled. So all these canisters are, we usually dedicate canisters to different materials, but all these connectors and hoses and stuff can be dedicated as well. Anything that's not dedicated to material needs to be cleaned out. So yeah, so storage bottles, there's all these fixtures. And so even after cleaning everything as well as you can, if you forget like one connection, I've had a technician tell me that even after I've cleaned the whole machine, I can get a teacup of material out of all the connections when I'm cleaning that, like go back and clean that system. So there's a lot of nooks and crannies that these powders can get trapped in. And then not only the printer itself, but all the support equipment, we dedicate our sieves to certain materials. They don't get cross-contaminated. But just think about any of your hardware that's touching the powder, all the O-rings, anything that might be exposed to powder needs to be either swapped out, dedicated to a certain material, or thoroughly cleaned. When you're transferring these materials to storage, there's a lot of connections. So to get the powder from this top canister to the bottom jug, there's about 3 different connections. There's 2 valves, one on either side. And then there's, I think there's another valve in the middle here. So there's a lot of different connections, just to make sure that you're aware that those can be sources of contamination. So as I said before, because of the high vacuum and temperatures in electron beam, the metallization occurs on the inside of the chamber. And so theoretically, this could be a source of contamination for other metals. You know, it could actually expose other metals to these elements. So just to be safe, we always clean out all of these parts. We bead blast any hardware that can come out. And then we grind down the surfaces that we can't remove, and then wipe those down with alcohol to remove all that grinding residue. Some pieces of equipment just really can't be changed, or just can't be cleaned out reasonably and doesn't make sense economically. So as we said before, the electron beam process centers the whole powder bed. So to remove that powder, you actually have to have to bead blast or particle blast that centered material around the part to get the parts out. So you may be thinking, how do you separate the bead blast media from the powder? Well, you don't. You use the same powder that you printed with as the blasting media, and you just reuse everything. But when you want to do a material swap, you can try to clean this chamber out, or since these run about $2,000, really not that expensive, you might as well just buy a separate system instead of doing a material swap. So if you have the space, this makes the most sense, and honestly, this would be very difficult to clean out anyway. So, but that's the type of thing you need to think about is your support equipment. So the list of sources of contamination is almost never ending, it feels like. So what we didn't talk about so far is, you know, any tools that you're using, so your brushes, your scoops, you know, you could even think about maybe even your screwdrivers and that kind of thing if you're using those on those systems. Any containers and funnels. Ensure that you can, once you start looking around your lab, you can just, you know, identify probably dozens of parts that, you know, could be sources of contamination. So my best tip is just to have, you know, have this on your mind as you're going, be in the mindset of continuous improvement, and really teach your technicians and find technicians that have that kind of a mindset, have that continuous improvement mindset. So with that, I think we will take some questions.
Thank you, Emma and Amy. Before we take a short break, we'll answer the questions that have been submitted through the Q&A platform. If you haven't already submitted your questions, now is the time. You can jot them in right there, and we will go through as many as we can now. So a couple questions have already come in. Is there anything that can be done to a feedstock that has been contaminated?
So I can take this one. I am not aware of much that you can do once it's been contaminated, and Emma, you can chime in as well, but it's very difficult to separate powders that have been mixed. It's pretty much impossible, and it's probably just not cost effective to go through all that. You probably just need to start out fresh. Obviously, there's some chemistry that we can try to do. We can try to reduce our powder if it's gotten oxygen in it, but there's really not, I'm not aware of standardized methods to do that, so that would be more of a research project. Emma, did you want to add into that?
Okay, great. Thanks, Amy. Another question that came in, while working with the same powder compositionally, but atomized in different ways, will one, say the gas atomized, be more dangerous than the water?
So that's a good question. Go ahead, Emma.
I was just like, so we can both talk to that one, and that, yes, definitely there is a difference in the surfaces of those powders. So with your inert gas atomization process, there's also gas atomization done with air. So there's some differences there too. So with inert gas atomization, traditionally you're not forming an oxide surface on the powders until after the powders have cooled down and you've removed them from the atomizer. And then you're bleeding in oxygen after the fact and letting those oxide surfaces form. So until those surfaces have been coated with oxygen and that oxide has formed, that powder is very dangerous. And a lot of times, even just in the oxygenating process, sometimes there'll be thermal runaway as that oxide forms. It's an exothermic process. And sometimes some of those bins will actually start to burn on their own, and they just have to take those bins out and set them out and let them burn off. And that powder is unusable. So that point is very dangerous with those powders. If it's kind of a more standard material like a steel or a nickel alloy, once it's been oxidized, it's generally very safe to handle depending on the size. Your water atomized powder also, just because of the water process itself, you're instantaneously forming an oxide on the surface using that water as a breakup. It's a source of oxide. And then so that in that way, you're making that powder safer. However, you're also forming a little bit of hydrogen when you're doing that process. And also you have a larger surface area because those shapes aren't just completely spherical with the water atomized powder. So that's a little bit of a consideration there too. And then if you have an aluminum powder or a titanium powder, which is much more reactive than your stainless steel or your nickel or your copper, those again are going to be a different consideration in terms of reactivity in the end. So do you want to kind of speak from your perspective?
No, I think you covered it. Thank you.
Okay, great. Metal powders have been around for so long. Are they a mature technology? What is the next area of metal powders?
Emma, do you want to take that one as well?
Sure. I mean, I think you can say yes to both. Yes, it's very mature in terms of how long these powders have been around and been used for these different applications, as even seen from Amy's case studies and some of the accidents. So a lot of those areas are mature in how those powders are used, such as traditional kind of metal injection molding of the fine powders to create parts, especially with the automotive industry. However, there's a lot of new areas opening up, and so I would say that again, it's not a mature technology because, you know, especially with all the new additive methods and new considerations on surfaces of powders and controlling those and alloys for these new methods, that there's a lot of development to go.
Great. Are there any reports available on the aging of powders in the additive manufacturing industry?
I guess I would ask for clarification there, whether it's aging or whether it's recycling. There are no reports that I'm aware of directly regarding aging of those powders as they're just stored or at room temperature, but there are a lot of studies done out there on recycling.
Okay, great. Another question that came in, this speaker mentioned nickel powder can get contaminated through the container. Can this issue be explained a little bit further?
With that, I was talking about a lot of nickel powders, just depending on the composition, in my experience, will tend to have kind of some electrostatic charging. And so those will tend to stick to the sides of the container. So then as you're trying to use those powders, you're maybe scraping off the side and then maybe scraping off some of the plastic of the container, depending on what it is, or if it's a steel container, maybe that's a better one to use because you can kind of discharge that more effectively and remove that electrostatic charging factor. So you just need to be careful and aware of the container and the material that you're using.
Okay, along contamination, can PPE be a source of contamination?
Definitely. We use disposable or dedicated PPE for the material that we're using. But yeah, absolutely on your lab coat, on even just your skin, if you're moving from, if you're not properly clothed and you're carrying powders from one machine to another, or you're doing two different jobs in the same day, that's just something to be aware of. You should be dressed out pretty cover as much of you as you can, and change your PPE if you swap materials.
Okay, great. Welcome back. We will now begin with the second part of the tutorial, powder handling for safety and quality. As a reminder, we will have Q&A at the end of the presentation, so feel free to type in your questions at any time into the Q&A platform. Emma, take it away.
Thanks, Diane. So now we're going to move into the powder characterization section of our webinar today. And as we've already seen throughout these presentations, that there's a high potential of powder characterization data to help enhance your efficiency and diligence, especially with regarding cross-contamination and powder changes as you're using those powders, and that a lot of those effects are critical to the innovations that are coming along within the powder metallurgy industry. So I'm trying to highlight with this presentation the use of relevant powder testing and how those characteristics can affect a typical production environment, and especially looking at those powder features that are changing with use or critical to specific production methods or specific consolidation methods, especially regarding AM. So with that, I'll move on to, which features are going to be necessary to monitor are going to be highly up to the particular material and the particular 3D printer or additive manufacturing machine. And then how accurate your data is and what hazards that are going to be present are really also dependent upon your use case and how accurate you need that data to be, and what material you're using for what hazards could be present. So with size, again, we talked about screening of those materials in order to classify and be able to use only the size powders that you want. But with screening, there can be effects like agglomeration of those powders, or you can break up some powders that have already agglomerated while you're screening. Also, those powders will be exposed to the atmosphere if you're screening within an air laboratory. And the reactions can occur within those powders on their surfaces as you're going through the screening process. But you can also screen within a dry box or a glove box if you have powders that are sensitive to the atmosphere. There are other methods of screening, other methods of size classification and size distribution monitoring beyond screening. So there's your typical stack of screens, size classification to give you a bell curve shape, but you can also use a laser system such as the CamSizer shown down here that will give you your size distribution as it's looking kind of at the cross section and shadow images of those features of the powders on a detector to give you a size. But again, your dry laser or your wet laser system might not pick up agglomeration of those powders. Those systems are typically assuming a spherical powder. So any off shape features that you have will not be identified necessarily. And then you also have potential that if you're using a dry laser, you're exposed to atmosphere longer, and is that changing your agglomeration or your size distribution through reaction? Or with a wet laser system, as you're dispersing the powder in the fluid for it to be measured, is that powder going to react with your carrier liquid or agglomerate within that liquid? So you need to consider whether you're getting your actual particle size measurements and how these are going to change your packing considerations, whether you're going to get a nice uniform powder bed within your AM machine or nice flowability features. And we'll talk more about that in a little bit. And does your chemistry and your phases change by your size distribution? And that's definitely been seen, and we'll talk a little bit more about those features. Again, smaller particles are going to react faster for AM and sintering applications that can give you a higher density, but also, again, additional hazards because of your higher surface area, so they can be more combustible and more flammable. And you can also get higher surface contamination. And did your distribution shift on recycling, which Amy already talked about. One area that we looked at too is being able to look at your particle size distribution in situ. So you could consider being able to do on-demand grab sampling during your powder process. I know many AM machines will have a build volume or a plan that you can use that will capture powders within a melted volume. And so you can kind of take that sample and keep it on hand as an archive for a representative distribution of the powders that you were using for a particular build. This is kind of an example of kind of a sample cup that you could insert into your process. And then there are also these in situ particle size analyzer instruments that, again, you're using a laser for your particle size and shape, but that can give you some real-time process feedback that may be beneficial for your particular industrial application or R&D program. When looking at powder characterization, shape, as I mentioned, is also very important. For getting an analysis of your shape, you can use light microscopy, which is really fast and gives you a large area, like in the image on the left. Or you can also use scanning electron microscopy, which gives you better detail and can give you some phase identification through energy dispersive spectroscopy. Again, your surface area changes with your shape, your flowability is strongly affected by it, and your attrition or agglomeration can happen. And the high surface area particles can be really fractal, such as kind of those off spherical shapes, and those can catch on each other and agglomerate, or catch on each other and cause lower flowability, or even catch on each other and break off small pieces and change your size distribution there, and simultaneously change your shape. So these are impacts that would affect your quality and your handling. When you're looking at your powders, your microstructure is also critical. You can use standard metallography and do mounting and polishing of those powders, like in the center image. Those are powder cross sections in an epoxy mount. But with mounting and polishing, are you getting pull out? Are you getting some loss by over etching your powder particles maybe? Also, your phase ID might not be consistent between powder batches because of your particle size distribution. If you're looking at larger particles versus smaller particles, your quench rate of those powders is different as they're solidifying during the process. And so you could have different phases or even different metastable phases present based upon how fast those particles cooled. So those pieces need to be part of your characterization and making sure your process is consistent and making sure you're getting the full information that you need for your particular application. Again, looking at using SEM, you can get some really nice images. These are courtesy of Tim Pro in our research group. And just looking at those surfaces can give you a lot of information in terms of, for example, on the upper right, these particles have a lot of what we call satellite features, which are those smaller spheres adhered to the surface of the larger spheres. And those happen when smaller particles are recirculated within the atomization chamber. And those particles can come back up and then come back in and be entrained within the atomization stream itself, and then deposit on those larger particles as they are cooling and being formed. And so you can see even just from this image that those powder features are going to have an effect on how those particles pack together, how they flow together, how they might center together if you're using a binder jet AM method. And images like SEM can help you identify those features and keep that as part of your quality control. Also, X-ray diffractions, common metallurgical method to look at your phase identification. But again, maybe you're exposing your powders to the atmosphere during that process. Maybe you're only getting the metastable phases that are present in the powders. And so you need to keep that in mind and maybe shield your powders, or maybe age your powders in a furnace or something like that, that might be relevant to the exact composition that you have. Just as a comparison, this is a study that we did in-house looking at some nickel-based superalloy powders. So all these powders are nominally the same composition and produced via atomization, but there are clear differences in how the powders have segregated, what the satellite features are, what their surface features are, and all of these powders then had different AM buildability and different build quality resulted from these powders. So these are from 3 different commercial suppliers, as well as 2 powders produced in-house on the Ames Laboratory Systems, as well as a prep produced powder on the bottom there. And you can see how there's different solidification features on the surfaces of the powders, different dendrite sizes. The white features on these surfaces are carbides, and so even just the carbon contamination and carbon level is different within these powders. Again, they were supposed to have some carbon in them, but the level is clearly different across the different suppliers and how those features are coming out on the surfaces, and whether or not they're large satellite contents or really nice spherical powders affected the flowability and then the packing density of these powders in the bed, and then resulted in different AM buildability. So nominally, you know, these are all the same size distribution and the same composition, but clearly all of that, the information on these powders is not captured just by those two criteria. So those are pieces that you may need to take into account when looking at your powder suppliers also. Another thing that Amy mentioned is internal porosity of the powders and how that is tracked in the AM builds through the build process, and that the porosity that's initially present in the powders is not eliminated during the AM build because of the violent convection in the melt pool. And so, you know, these are things that you can't see just by looking on the outside of your powders. These are features that are trapped on the inside. And so in this case, these are some powders that have been looked at by Dalit Singh at Argonne National Laboratory using the Advanced Photon Source. And he's collaborating with us on a current project and took these images to look at the internal porosity within these powders. All the scale bars are 100 microns, and you can see some similarities across these different powders that were produced by a commercial partner. There's some difficulty in getting these images processed, and this is a active area of research, but you can kind of see how you move through and get the black and white images and then do an image analysis to look at the powders that have these spherical pores on the inside, and then characterizing those using some segmentation methods. And so here he's characterized those samples and given the porosity percent as the total volume of closed pore divided by the total volume of the powder particles themselves that were present in the sample. And so it ranges from 2% up to almost 4% within these samples. And these were provided by the same commercial partner. So even just within batch to batch, you can get some variation of the internal porosity that will stick within your final powder produced part. Then it's not just the volume of that porosity, but it's also the size of those pores. Smaller pores versus larger pores, and then the resulting pores that will be present in your final part. And so there's a difference in the number of the pores and how those are present, and not just the size, but then potentially the shape of those pores. Are there different shape features? And then even compared across different processing methods. So all of these powders were produced via close coupled gas atomization. However, the different processing parameters, even using the same exact atomization system, can cause a wide variation in the internal porosity. And again, this is volume of internal porosity versus total volume of pores. So even within our own system at Ames Laboratory, we were able to get close to 0%, but then as high as about 1.5% of internal porosity. And then even amongst the commercial, again, going from about 2% up to 4%. So, you know, those internal porosity measurements can also potentially be critical to your process, or to maybe even advertising your powders for a potential customer, and being able to characterize your powders as having lower porosity and then resulting in a higher AM build quality. So then not just the internal features, but also, again, we've talked a lot about the surfaces of these powders, as powders are a large surface area material, that there are surface area measurements that are geometric, which are just image dependent, but you can also do BET, which is more accurate, and that's shown on the bottom how you're doing gas deposition on the surfaces and getting mono layers, and then filling in your surface pores to get you your full surface area measurement through increasing pressures. And again, your shape changes your surface area, your reactivity increases with your area, and any fresh area that's formed, maybe as you're mixing these powders together, will cause potentially reaction as those oxides or whatever other surface might form, and can cause degradation as well as heating of the powders, and something that you need to be careful of. Another measurement that we found really helpful actually in-house for measuring and characterizing our powders is actually Auger electron spectroscopy. And this one isn't very common across the industry, but I really hope that it becomes more so. And this is where you have an electron beam measurement where that electron beam is going onto the surface of the material, and then the detector is picking up the Auger electrons that are coming off of those atoms, and then you can use an argon plasma to etch away the surface so you can get a depth profile of the material itself. So here, again, are different commercial powders as well as some produced at Ames Laboratory. But again, same nominal composition, but a wide variation in the surface oxide thickness and composition as a function of penetration of the material. And the X scale bar there is in nanometers. And the intensity level is just based upon the intensity of the counts. And then the blue curves are your oxygen data. And then these are nickel, aluminum, chrome, and titanium curves for elemental compositions on that are increasing in the green and the blue colors. These powder particles were measured 8 powder particles per batch to get some statistics behind these measurements. And then these profiles were analyzed using an sigmoidal function fit to get a midpoint, and then analyzed with some error bars, obviously, too. But just even amongst these same powders, there's a significant difference in not just where that kind of D50 crossover point between those two materials of the oxide and the internal bulk metal composition of the powder particles, where that crossover happens, but also just the profile of the oxygen into the material and how steep that curve trails off, or how smooth it trails off, and that can indicate a more diffuse oxide layer that perhaps would be more conformal versus a sharper interface between the oxide and the powder particle interior, which could mean that powder might be more prone to that oxide flaking off, or being more brittle, and then being able to form new surface area. So that might be a measurement that could be informational for looking at your powders and comparing them, and also looking at your quality control as you recycle powder and continue to look at it. And then again, just a comparison of those numbers across the different oxide surfaces. Another measurement that is gaining popularity is looking at the electrical conductivity of powder beds. And this is a paper published by Montes in the Journal of Materials Science. Again, apologies for my dog. And metal powder beds, their electrical conductivity is critical, especially for electron beam additive manufacturing. And so the electrical properties have an effect on the buildability. Like Amy mentioned, that those powder beds are actually sintered together. So this could be used as a potential screening procedure or a measurement to accompany your powder characterization data in order to be able to characterize this powder as buildable or not buildable. And this is based on a 4-probe conductivity measurement that's pretty common across the industry for conductivity, and then modified for a metal powder bed analysis that gives you some conductivity measurements. And it's variable according to your force, your temperature, and your probe frequency, but you could develop a standardized test method for your particular workflow that would give you information that's critical to the process. Another feature that we've talked about is flowability. And so some of the standard methods that have been around for a long time include the Hall funnel or the Kearney flow meter for high flow powders. But there are also new methods out there, such as powder rheometers, that give you kind of a no flow to a flow transition, or a cascading avalanche for low flow powders, kind of with a rotating drum and giving you an avalanche angle as that drum rotates. There's also different flowability measurements based on different use conditions, whether that's temperature or humidity, and that can change your measurements for your flowability. For example, with this powder rheometer, there's a kind of a propeller that goes through a set volume of powder, and it measures the resistance of the powder to flow for that specific powder bed that would be in motion. And that resistance is correlated back to particle motion. And this particular setup can give you a lot of different information from your powder bed, including your bulk flowability energy, your powder-powder friction, your powder wall friction, your surface roughness, your moisture content, different size and shape effects, as well as electrostatic charging, like we talked about with nickel powders, and potentially charging to a plastic material. So just as a comparison here, there are 2 different pure nickel powders, as well as a nickel-based superalloy, which is the Mod 2 pink curve there. And this measurement kind of gives you an indication of the stability of your powder as it undergoes continuing flow measurements. And that's the first 7 measurements within this scale. And then at different flow rates, it can increase the energy required to make that powder flow. So in this case, the pure nickel powder evidenced electrostatic charging. All these powders had fairly uniform stability of the flow rate, but then again, as the speed of the propeller was increased, that actually showed a greater resistance to flow at lower flow rates. And then just even kind of a qualitative comparison, not quantitative comparison, to a titanium 6-4 powder, you can see that those the bulk flowability energy especially is different for titanium versus nickel in this case, and that can give you an indication on how this powder might perform in your powder bed or your directed energy deposition AM machine, and how if you're switching from materials, you might need to be changing your approach. We've talked a lot about reactivity, and Amy is going to follow on from this presentation a lot more in the safety aspect, but we've mentioned that the surface area changes, that there can be rapid heat generation with pyrophoricity and explosivity, as we've seen with fireworks recently on the 4th of July. And then all of your flare materials or lighter flints are typically powders. And then, you know, there can be combustion or degradation of these powders, whether they're being stored or transported, and need to be dealt with appropriately. One example that we have done in-house, as I'm wrapping up here, is just magnesium powder flammability. And traditionally, you would think of, for example, magnesium to be one of the higher reactive materials. All of the materials on the left side of the periodic table, again, increasing reactivity. However, with this powder, we were focused specifically on the surface as we were atomizing this powder, and made an oxyfluoride coating rather than just an oxide coating, as the oxyfluoride is more stable than the oxide. And so in this case, the demonstration here is showing a heating profile of the powder in a furnace, and the commercial magnesium powder ignited at about 525, but then this powder with the oxyfluoride on it didn't ignite till 635. And so that's almost the melting temperature of magnesium. And so these powders were extremely stable with that oxyfluoride coating. So even though you're working with a specific material that you may think is traditionally explosive or non-explosive, how that powder has been produced and how that surface is been changed or modified or controlled really can affect your flammability. So in this case, the powder is extremely stable and would be more stable than many of the traditional powders that we would deal with. And just as an example, another piece that we test with any of our powders coming out of the atomizer is doing what we call a spark test. So these are the same size powders, and then they're exposed to a Tesla coil. The powder that was created with these oxyfluoride coating did not react. And then, so we kind of rate that internally. We just have a comparison scale, 0 for non-reactive, and then the commercial powder immediately ignited, and that flare propagated. So that would be a 5 rating for highly reactive. So this could maybe be something that you incorporate to your process, whether that's powder as you're pulling it out of the machine. You check the flammability and how that's changed, and whether it's safe to handle, or whether you need to be and normal to handle, or whether something happened that you now need to take extra safety precautions for. And again, this test is pretty easy and quick to do, which is why we use it as just a comparable scale for measuring our powders. So with that, I will hand it back over to Amy.
All right, thanks, Emma. Okay, so now we'll dive into our powder metal safety. Just forewarned, this is the basics. We're not going to be actually advising you on how to do your operations, but we just want to give you the basic knowledge to understand the hazards that you're going to see with powdered metals. So like we said before, there's a lot of processes that use metal powders, such as metal injection molding, conventional press and sinter, tipping. And then, so there's a lot of standards in those industries for handling those metal powders. But now that we have metal powders in additive manufacturing, such as laser electron beam, we have the lens process, which is directed energy deposition, and binder jetting. It's kind of this new industry that's developing that the standards aren't quite as mature as they are in the other industries, and there's some different things going on in those processes as well, we'll talk about. So just you will find this useful if you're a researcher or an engineer and you're new to powder processing, you're setting up an additive manufacturing lab. If you're one of these people looking, working with your health and safety personnel, and you're trying to establish safety procedures, these this section will help you kind of get a foundation for that. If you're a safety personnel and you're working with metal powder for the first time, this can give you some of the language that you need and some of the things you need to look up. And then also any manufacturing companies that you're getting into AM. So in terms of hazards, we're not talking about quality anymore, but just hazards. There's 3 different reasons powders can be hazardous. Their size, the smaller they are, the more hazardous they can be. Their shape, so the smoother they are, the better. Some of them can be jagged though. And their composition. So for size, we have reactivity. If they get small enough, they can become a breathing hazard. For shape, we're mostly concerned with our breathing hazard damage to our lungs. With composition, that reactivity and toxicity. So as we said before, the powders just have so much more surface area for reaction. Just to illustrate that point, if you take a 1-inch cube, the surface area of that is going to be 6 inches squared. If you took a 1-inch cube of powdered material, 100 micron powder, it's over 800 cubic inches. So that's more than 2 orders of magnitude difference in surface area. So powders, as we said before, are ignitable. So not only are they reactive and they can be ignited, but because of their size, they can travel, and that becomes an issue as well. So the hazards associated with smaller powders, so we're talking about 10 microns and below, they can travel further through the air because they're lighter, they have more unpredictable motion, and they have more surface area. So it's kind of becomes almost an exponential issue once you get down to those sizes. Larger powders, like 100 micron powders, they do flow more easily, but that also means that they'll spill further. So if you have a spill on your floor, you could, imagine these things as tiny little ball bearings, just, making their way across the floor. So that's an issue for safety as well. You could find maybe some corners of your lab that are collecting powders. They do settle more quickly and they do have less surface area. So in general, the larger powders are less of an ignition hazard in general. So why metal powder ignition is exceptionally dangerous is because metals have high burning temperatures. So not only once you start a metal powder fire, not only will your powder be catching fire, but other things will be catching fire too. So I believe the ignition temperature of aluminum powder is around 600 Celsius. So you can imagine a fire burning that hot, it's going to catch, maybe the rest of your machine, your panels on fire, any plastic that's around, computers, concrete, metal structures in the building. It could just really get out of hand. The high surface area of powdered material makes it the perfect reactant, as we have been continuously emphasizing. Just that's the main thing to remember. So this reaction will happen very, very quickly, and it's exothermic in nature, so it's self-feeding. So that is an important thing to understand. Is once a metal powder fire gets going, it's pretty almost impossible to put it out. So that's the next point, difficult to extinguish. So if you put water on this, that's probably the worst thing you can do, because as we said before, in water atomization, the water actually supplies oxygen to the metal. The metal will rip that oxygen right out of that water molecule, and you will just make things worse. So one of the ways to properly extinguish a metal fire is salt extinguisher. So this salt will deposit over the metal fire and it will melt and isolate that metal fire. Anyway, so that's just one method. And so the other major hazard, and this is what has caused all these explosions, is that the initial fire or combustion or spark can disperse that powder into a cloud. And then there is a secondary explosion because of that initial event. And so we'll talk about that, what that looks like. Yeah, so just to reiterate the point, metal burns hot. So like I said, aluminum is around 760 degrees Celsius. You got steel. If you have a steel fire, that's going to be very, very, very hot. And then some of these other materials as well. And again, rocket fuel is metal powder, so it burns very, very hot. And here is that that fire triangle. So this is for a normal fire. You need oxygen, you need heat, and you need a fuel source. The dust explosion is more of a pentagon, so you do need that ignition source. You have your fuel, which is your dust. You have your oxygen, your air, but generally you have some confinement. So there's the container that it's in, the 3D printer that it's in, or the building that it's in. And then you have a dispersion of it in that confined space, and that's your recipe for an explosion. And this is how it occurs. So you have your initial event, so you have a spark, and you've got some smoldering happening, and then what that creates is the cloud, and then that cloud will ignite, and that is the explosion that does the most damage. So that's kind of how these powder explosions go down. So just to share with you a case study of how this type of event can occur, this is in a powder manufacturing facility. So this is a facility where they actually atomize these metal powders, and this is actually in Tennessee, so kind of close to home for me. So anyway, there was this metal powder manufacturing facility where they obviously were not very clean. You could see how much dust had collected in the rafters and just all over the equipment. And so during operation, obviously, if you have a fork truck moving through the facility, or just general moving through the facility, and people walking around on stairs, that kind of thing can cause dust to gather in the air. And at the same time, what happened is maybe this motor had been not serviced, or it just was exposed and it shouldn't have been in general. But as that motor turned on this piece of equipment, it created an arc, and the arc sparked this massive explosion. They've actually had a couple explosions at this facility and deaths associated with that. And so this is the type of scenario that most people are aware of in these metal powder explosions. And so I tell you that case study to make you aware, but in reality, your additive manufacturing facility is going to look nothing like a metal powder manufacturing facility. But you do need to be aware of these, because these are the case studies that your safety team will have access to. This is what they will be concerned about. And so these are the situations that drive all the building codes, the handling procedures, and other fire protection that you do have to follow. And so we'll discuss those. So we do need to understand, getting into these terms that you need to understand for the hazards. So we talk about the reactivity of metal powders. So there's two different types of reactivity that we want to talk about. The first is combustibility. And what that means is if I have a pile of powder that is ignited, will it continue burning? So that's combustibility. Explosibility is if I have a suspended cloud of powder and it's ignited, how much pressure change will occur? So how much power is going to be behind that explosion? So explosibility and combustibility. There are standardized tests for this, and you don't really necessarily have to do these in-house. In fact, it's really just easier to send them off to people with these pieces of equipment. But there's an ASTM standard for this, and they'll form a dust cloud in a combustion chamber. So like the one that you see here, they'll ignite it using a controlled amount of energy, and then they record the pressure time curve. So how fast does the pressure rise? how much pressure is created. Basically, again, what is the power behind that explosion? And then they just have this metric. If it's, above this number 2, it's explosible. If it's below, it's not. The combustibility test is also standardized. So you can see the National Fire Protection Association and FPA guidelines. It's in FPA 484, section 5.3. And the way it dictates it is that you will lay down a line of powder and you will ignite one end of the powder and see how fast the flame, the ignition will travel along the line of powder, if it travels at all. So if there's no reaction, that's considered non-combustible. If it glows, but it doesn't propagate along the powder train, it's non-combustible. If we do get propagation along the powder train past where you started the ignition, it is combustible. And so here's an example of some materials that we had tested and what those reports look like. So we had some copper powder analyzed, and after these tests, it says for combustibility, the sample material shall be considered to be in a non-combustible form. So that's good. That means if a pile of this powder was ignited, it wouldn't propagate. Explosibility, it says the sample material is not capable of ignition of explosion when suspended in a dust cloud. So that was good news as well. This titanium carbide powder, which I had always thought, oh, carbides, that's a stable ceramic. It's not going to be, necessarily as dangerous. But when we got these materials sampled, it says it's got limited combustibility and it is capable of ignition and explosion when suspended in a dust cloud. So when you get these reports back, this is what your safety team will be looking at, and this is how you will determine how you handle these materials and how you maybe don't want to handle these materials. So once you understand the risks, the combustibility and explosibility, here are the controls that you need to put in place for fire prevention and containment. So we'll talk about bonding and grounding of equipment. So bonding and grounding is so that one of the major concerns for having metal powder and handling it is not only sparks from equipment, which should be avoided at all costs. These computers should be sealed up; they should not be exposed to metal powders. Any motors that can arc or switches, all these things need to be properly grounded. But then any metal pieces or any pieces of equipment or parts next to the powder that could be, when you touch it, has a static spark to it. So remember, think about in the winter as you walk across carpet and you touch something metal. That static shock is actually a concern for creating a metal powder fire. And so because of that, all the equipment, all the metal pieces on the equipment need to be bonded to each other electrically. So wires, physical wires, bonding all these pieces together. And then that needs to be grounded to earth ground. I'll show you some examples of that. Also, you want to limit oxygen exposure when appropriate. When you store these powders, they should be sealed off so that if something were to happen, they don't have just a ton of oxygen to access. Your building codes are also a driver for what you can and can't handle. So the building codes will dictate how much of a hazardous material you can handle. And that's because if you have an explosion, your building needs to be designed such that if the walls blow out, you don't get a whole total collapse of the structure. And then your general safe handling practices as well, metal scoops and that sort of thing. So bonding and grounding, like I said, every little piece of metal on the machine needs to be electrically bonded to either the frame or your grounding strap. And that ground needs to go to earth ground. And so you can verify this by taking just a multimeter with the conductivity beeper on it. And you can see if you have conductivity between this metal part and your earth ground. And so this is our building column here that we've got our earth ground connected to. This building column goes down into the concrete pad of the earth, or next to the earth. So when you do this bonding and grounding, you can't just put a bolt into a piece, a panel if it's powder coated, if it's painted, that's not going to be conductive enough. So you have to actually grind that paint or that powder coating off to actually get a good electrical connection. And so we were just trying to get our bonding and grounding done really quickly. So we would tie all these individual bolts on a machine together using wires. More recently, we've gotten smarter and just ground that paint away instead of actually wiring those together. You live and learn. So I want you to see if you can spot the bonding and grounding in these machines. These are actually pictures that you had seen before. But if you look closer now, you'll be able to see the bonding and grounding. So here on the left, in this laser powder bed machine, you can see this green wire that's kind of snaking through the machine and then attached to the door on the very lower left of that left-handmost picture. In the middle picture, you can see the green grounding wire coming from the top of the machine to the bottom, and that's hooking into different pieces of the sieve to make sure every part of that is bonded and grounded. Okay. And in this electron beam machine, the window, it's really tiny little wire. Since it's so hot in this machine, the wires aren't coated with green, but the window actually has a small wire on the door to connect that shielding cover that opens and closes the window to the door. So all of these pieces have to be bonded and grounded to ensure that nothing sparks static ignition. I guess I could have pulled those arrows up earlier, but now you can see clearly where this bonding and grounding is. So let's dive in specifically to aluminum. There's a lot of movement in aluminum and additive manufacturing right now, but aluminum is kind of its own special, exceptionally hazardous material. So the reasons why it's so hazardous compared to other metals is it's very lightweight. So it travels far and it stays locked in. So even if the powders are the same size as another feedstock, it's gonna just be a lot harder to keep contained. When you open some of these containers, you will see dust coming out of them just because, maybe it got tapped a little bit. Aluminum is so much more reactive than most metals. And it's just, like I said, it's gonna be its own kind of beast in terms of building procedures and making sure you're handling it safely. So when you're handling aluminum, these are kind of the extra mile that you might have to go in terms of engineering controls. So not only bonding and grounding your equipment, but you'll need to bond and ground your operators. So you can do that by putting in conductive floors that are bonded and grounded. Your operators will wear conductive shoes that are grounded to their skin, and those will be conductive through the floor. You will use all conductive materials, all your scoops, brushes, containers, hoses, everything will be conductive. And then you will make sure that your powder is always in an inert atmosphere. So in case something does happen, there won't be any oxygen to feed that reaction. So these are the kind of extra things you have to do when you're talking about aluminum. So let's talk a little more about inert atmosphere processing. So like we said, that's a preventative measure against ignition. So if there's no oxygen around the powder, there's no oxygenation, no burning, no ignition. Typically, we will inert the atmospheres or inert your container or inert your glove box with nitrogen or argon, depending on the material you're using or depending on your budget. So, nitrogen is going to be a little less expensive than argon. And it really, as Emma mentioned before, it actually is required for certain metal powders. If you want to maintain their quality and chemistry, you'll be doing this anyway, not just for safety. But as Emma had also pointed out, your powder is much more reactive. So if it's got this nice non-oxygenated surface, that surface is primed and ready to be oxygenated. So as soon as there's any kind of break in the seal or any exposure to atmosphere, it's going to oxygenate. And just by being exposed to oxygen, it can actually ignite itself. So just typically in additive manufacturing, you will be, depowdering your part or dealing with the powder in the printer with glove box gloves. So this actual door here on this printer will have through holes for gloves so that you can make sure you're handling your powder in an inert atmosphere at all times. So yeah. So here are some building codes, just to overview. So this, again, this is in NFPA's document 484. And this is the type of things that they're looking for in a building that you're processing metal powders in. So dust collecting surfaces should be angled, easy to clean, or have smooth finish or paint. So this is when we talk about rafters in the ceiling, those are collection points. Walls can't be unfinished. If you have just like cinder block walls that aren't painted, those can be collection points for dust. So you need to, be aware that the cracks in the floor can be collection points. And then, like I said before, your walls shouldn't be load bearing. And this is, again, these are the codes for typical metal powder handling. So let's see, ceiling girders I mentioned. And then windows. So there's special ratings for windows for these types of facilities. And the idea is that if there's a massive explosion, they will behave a certain way to minimize the damage, basically. And there's venting that is needed as well. So if there is an explosion, the facility can vent instead of the structure taking the brunt of that force. And then also there's, maximum amount of powder you can store and process it. And so anyway, but storage and processing requirements are different from each other. So again, back to some case studies. We want to keep ignition sources or heat sources away from our metal powder. There's this, kind of old wives' tale about somebody opening a can of metal powder with an angle grinder. So obviously that's not, that was a result of not properly training someone about the dangers of metal powder. You don't want to expose any of your electrical connections or circuitry to metal powder. If you have outlets near your machines, that might be something you actually want to remove. If they're not covered, you want to use your smallest quantities where possible. Don't let powder accumulate. You want to make sure you're practicing proper hygiene in your lab space or your production facility. And then again, back to that point, is train your personnel in this hazard associated with metal powder. This is something that it's kind of a sleeping giant. Once it's awakened, it's a big deal. The accidents that happen with metal powder are big ones. And they don't seem very intuitive, but it is very dangerous. And so this is just another case study of a whole facility that was destroyed because of an incident with poor employee training. And so investigation found that the company did not institute procedures such as combustible gas monitoring or provide training for employees on avoiding flammable gas fires and explosions. So we've talked about all of the fire and explosion risks associated with powders. And now we need to talk about the breathing hazards. So this is the actual effect on your lungs. So the hazards associated with powders in your lungs and breathing are physical damage to your lung tissue. So your lungs are a bunch of very small channels, and if you get powder, if you damage the very delicate tissue of the lungs, and in some cases that cannot be regenerated properly or it doesn't get regenerated, you can damage the little fibers on the surface of your lung tissue that actually is what moves the mucus around and out of your lungs and cleans your lungs out, and that's an issue that can cause mucus buildup and lead to chronic illnesses. Also, we can absorb toxic materials through our lung tissue. And so we want to avoid powders in the lungs at all possible. And so we have these long-term issues called silicosis and asbestos that are some of the long-term health issues. Also, obviously, we want to avoid absorption through skin, but with proper PPE, that's usually pretty easy to avoid if you're diligent. So like I said before, Mechanisms of lung damage is scarring of that lung tissue, those alveolar sacs, which are those very, very tiny channels. That causes also inflammation and loses elasticity. So basically just degradation of your lung function in general. And the destruction of that cilia, those fibers on the surface of your lungs, that causes the mucus buildup and that infection. And so repeated destruction, so if you have chronic exposure to dust, that leads to abnormal cell behavior. So even if it's not like a radiological cause of cancer, just by damaging cells and making them regenerate more often than what their normal life cycle is a cause of cancer. So this is actually very carcinogens actually apply to a lot of different types of situations. We talk about carcinogens, so this is the worst case scenario and not necessarily what we would ever see in metal additive manufacturing, but this is asbestos, and the chemistry of the asbestos is not cancerous. It's not an issue, it's not toxic, but it's the shape here that makes it so dangerous. So once this gets into your lung sacs, it clings there. These hook-like structures just cling in place, and you can't get them out, and they do repeated damage. So once they're in there, they just keep repeatedly damaging the lungs, and that is why this is a carcinogen. So here's just some different particle shapes. So this is jagged, so this is our asbestos and jagged quartz here, and then lunar dust is another example of a carcinogen. Not that we have to worry about inhaling lunar dust, but I did have to work on lunar dust for a project, and we had to go through a lot of training on how to handle that safely. Just fun fact, lunar dust is the shape that it is because it doesn't move, right? Like it's not blown by the wind or jostled around, so it maintains its jagged shape. It doesn't get smoothed out. So here's the type of shapes that we're looking at in metal additive manufacturing. So probably the I don't want to say ugly because all powders are beautiful, but the most irregularly shaped powder is this water atomized powder here on the left. So it's got some really irregular shapes, and so that would be a little more hazardous than these like nicer spherical powders. So typically in terms of shape, we're not necessarily worried in metal in additive manufacturing, but particle size is still the issue. I actually have handled silica-based material, so silicon carbide is a material that we use in binder jetting that you wouldn't typically see in metal powder AM or just powder bed fusion. But we had to learn about the unique hazards of silicosis. So silica, the particles that are coming off of things that you grind that have silica in them, the shape isn't necessarily the problem. The size is a problem because it gets in your lungs. But the main problem is that the dust does not get absorbed once it's in your lungs, and it just stays there. And it's not necessarily doing a ton of damage, but it's there and it doesn't go away. So silicosis is actually very, very dangerous. There is this article here that I found. It says, back before the Black Lung, the Hawks Nest Tunnel disaster killed hundreds. So hundreds of people died. And I remember my grandfather telling the story about how they would just keep sending people into this tunnel to work, and they would just keep dying and dropping like flies. And this is before they knew about silicosis. And so that's how deadly it is. It's just, a few days of exposure and, you're done for. So this is why whenever, just a tip for health and safety at home, if you're ever grinding tiles or any, kind of home projects where you're actually having to cut these materials, you do need to wear lung protection. And like I said, we had to do a lot of work around protecting us from silicosis in our lab when we were dealing with silicon carbide. Okay, so that is the breathing hazards associated with powder materials. Now let's talk about toxicity. So just up front, we'll talk about some of the common, most dangerous effects of common metals. So if you inhale nickel powder, the risks are chronic bronchitis, reduced lung function, and cancer of the lung and nasal sinus. Inhaling aluminum, you'll have lung problems such as coughing or changes that show up in chest x-rays. Some workers have decreased performance in some tests that measure functions of the nervous system. So we know there's some connection between aluminum toxicity and the nervous system. Chromium, there is a condition called chromium-induced asthma. There's you can have ulcers in your nasal septum, chronic rhinitis, chronic kind of like allergy symptoms, and then bronchitis. So these are things that we don't want our technicians or ourselves to have to endure. So there's an argument about toxicity of the actual pure element metals. They're more simple compound forms, and the toxicity in alloy form. So here is a report about the bioavailability of nickel in alloys. So what they found, they don't believe that the nickel is bioavailable when it's in alloy form. And so they're proposing that the exposure limits, the permissible exposure limits set out by OSHA and NIOSH to be, take that into consideration. So there is this argument out there that once your nickel is in alloy form, or once these metals are in alloy form, they're less hazardous, which, you know, a prime example of that would be stainless steel. We know that that's safe for the body. However, other studies show that there's a study on rats that showed one of the nickel-based alloys, which was approximately 66 nickel, 13 chromium, 7 iron, was tested independently in 2 laboratories using different species, and it was found to be carcinogenic in both studies. So you can try to argue that, hey, I'm working with a metal alloy, so I don't need to worry about these toxicity issues. But in my experience, this is NIOSH and OSHA are the governing voices on these, so I would just refer to what their permissible exposure levels are. So how do you determine your exposure level if you're dealing with a metal powder? So the standard method is your breathing zone test. So this is a little device that gets strapped onto your operator and pumps in air around their breathing zone. So maybe it'll be like on their shoulder and next to their face. And as they're working, this will be sampling the air and breathing like a person would. And so obviously when you're doing this test, you don't know exactly what the exposure level is. So your operator will be in a face mask or respirator, depending on the severity of the hazards with that powder. Will determine the PPE that they need to be in. The reason you would do this, and the reason we've done it in the past, is that there were certain machines and operations that we're doing that we didn't necessarily want the technicians to have to be in a respirator. We had certain policies that we can't reuse respirators, so they have to be. Anyway, it was an expense, and it was also the technicians weren't necessarily fond of the idea of having to wear these respirators. So this is when we would do those testings to see if we did need that PPE. So this is a PPE. These respirators, you think, oh, this is an easy solution for my metal powder safety, but try wearing a respirator for more than an hour, more than a few minutes at a time. They're very uncomfortable. Your technicians are not going to be happy if they're not used to wearing these. They're not going to be happy about having to use them. It's just, it can be, there's pros and cons. So obviously the pro is that you completely protect their breathing zone with these respirators. If you have a full face mask respirator, they're protecting their eyes as well. Again, the cons are they can be very expensive. And so again, when we're talking safety, we got to balance cost and benefit. And they also just can change the attitude towards carefulness and cleanliness. Sometimes I know when I'm wearing a respirator, I just kind of want to get done with what I'm doing as fast as I can because I don't want to be in this respirator. And so maybe I'm not being as careful. And so our attitude at our facility is that our ventilation and our actual setup on whatever job we're doing is the first line of protection, and then our respirators are the second line, just to have that redundancy. Also, the issue with respirators is that if you don't have isolated areas, anyone walking by that doesn't have a respirator on is not going to see the same protection. That's why we do engineering controls on our equipment first off. And then you still have that eye and skin exposure if you're not using a full face respirator, and they're cumbersome. So these positive flow full face respirators are coming into vogue. I'll give a shout out to my colleague Ed Tackett at the UL Auto Manufacturing Competency Center. He's been a big proponent of these masks. I hear they're super comfortable. Instead of you having to pull air through a filter and having this thing this mask just tightly cinched onto your face, these helmets, I guess you could call them, will flow clean air over your face and create a positive pressure environment into your breathing zone and over your face, so that you can breathe freely, and it's cooling your face at the same time. So you're not getting sweaty and icky and hot with those full face respirators. So I'll just take a shout out to his course. They do a very, very extensive multi-day course on metal powder safety that gets a lot deeper than what we're offering today, obviously, because of time limitations. And then just normal PPE, as you would expect for any kind of lab environment where you're handling chemicals. You want to make sure you have gloves, lab coat. It's a good idea to tuck your gloves into your lab coat. This guy doesn't necessarily have that happening, but that's something to do. Goggles or safety glasses. Obviously, goggles are going to protect you better from powder in the air. And then consult your safety personnel if you can use disposable PPE. So these kind of fabric lab coats are nice, they're eco-friendly, but that contamination, and also just reusing coats over and over again and maybe not washing them enough would be a hazard to you as well. So I'm going to switch gears a little bit. So one of the unique things that you have to think about if you're getting a laser powder bed system, there's some unique things to consider about the safely operating that equipment. We're going to talk about safely changing the air filter in your laser powder bed system. So that might not be something that you would think about as an issue, but that is actually a very hazardous procedure to change that air filter. So we'll talk about that. And then how you're going to clean the recoder and dispenser, and how you're going to clean that hopper. We'll do that safely. Okay, so let's talk about this air filter. So when you're melting in a laser powder bed, you have sparks coming off of that welded powder. I guess if you've seen metal powder being welded, you know what I'm talking about. There's those sparks. In laser, there is an air knife that is collecting that spark. It's passing over the powder bed and pushing all of those sparks into this air handling system that pulls it through this filter. So this filter is just a diesel engine air filter, basically, and it gets all of these now nanoparticles. The soot is actually nanoparticles of metal caught in this paper filter. So in the printer itself, this is in an inert atmosphere, so we're relatively safe. Once you expose this paper filter full of nanoparticle metal to air, this is an explosion waiting to happen. It's fire waiting to happen. It's happened to us, and it's something that needs to be worked out. But we have procedures to safely replace this filter that I'll share with you. So the main thing is, so never expose this thing to oxygen air. So what we do is we remove the canister with the filter inside out of the machine. To do that, there's seals on either side. So you close it up, take it out of the machine, and then we have this setup where we have a jug of water that has these markings on it so that you can fill this canister. So it's inerted, and then you put this jug of water on top, you open the valve between them, and then as this water is rushing into this canister, the inerted gas is bubbling out. So you never actually see atmosphere into this thing. So as the water is entering this canister, it is reacting with that metal powder, because we know that Water has oxygen in it, so there is reaction, but there's so much water in relationship to the amount of flammable material in there that it cools it down. And basically, this is how you can inert that situation before you are exposing it. Inert that situation and just eliminate the hazard. And then important part is that you purge with argon before reinstallation, just to make sure that as you're getting your system up and running, that canister is not filled with atmosphere. Okay, so that's just really important to know. And as you know, if you're looking to get a laser powder machine, this is not a trivial thing when you're changing out these filters, and I think they have to be changed out monthly. And so anyway, this is something you really do need to think about, and we actually have like a dedicated area for filter changes. So we have talked about sources of contamination and cleaning. These filter, I kind of feel like these slides should have been earlier, I apologize. But anyway, so this is that hopper, that dosing mechanism that you take apart and clean. And then this is that hopper with the powder. So we will take that out and wash that and wipe it down with alcohol. Okay, so we have talked about all of this. Okay, so just getting into cleaning, hygiene, so that's part of safety as well. Just think about, as you're operating these systems, you might start noticing powder collecting in different areas. So just be cognizant that, your floors, your walls, your computers, electronics, your tools, any horizontal surface basically can be a source of collecting powder. So you need to make sure that you clean that often. The way that we clean for safe cleaning is we use those Swiffer dusting wipes. So you really shouldn't be spraying chemicals. So no cleaners should be sprayed onto these metal powders. Those can actually react as well. They can have different reactions based on material. We will use these dry Swiffer wipes and then just throw them away. So we have boxes and boxes of these laying around. We find that's the best and safest way to collect that dust. The wet wipes can be used if you know your material is inerted. So when we're running ceramics on binder jet, we'll use the wet wipes. And then vacuums. So vacuums are appropriate in certain situations and are pretty much the only way to do it. But you have to consider vacuum safety as well. Vacuums can also, if you're using a vacuum recycler, you'll have to have a dedicated vacuum for each type of material. And then you need the appropriate explosion-proof vacuum. So we talked about this. So dry vacuums are bonded and grounded to prevent that static buildup, and they must be grounded during use. So that's not just plugging it into the wall. There's actually a separate grounding strap that gets plugged into your grounding column in your building. And then these store the powders dry, so it's not safe you just can't use dry vacuums for reactive powders, certain reactive powders. So when you have reactive powders, you have to use what's called a wet vacuum. This is also bonded and grounded, but the way it works, similar to how we were inerting our air filter in water to make sure that it doesn't combust. This wet vacuum will submerge your powder in water to make sure it is oxidized, fully reacted. And these are actually a high maintenance piece of equipment on their own, and they do need to be monitored and emptied regularly. I know that the equipment suppliers are more than happy to provide you with those procedures, but this is not something that can be neglected. In fact, there has been a very serious incident with a laser printer operator who got third-degree burns, life-threatening, because the vacuum was not properly maintained. So that is a lot of information. Just as a review, we've gone over the difference between combustibility and explosibility, how you test for that. We've talked about engineering controls against those hazards such as bonding and grounding, keeping your atmospheres inerted where appropriate, your building codes that you need to be aware of, the National Fire Protection Association 484 report. We've talked about the hazards associated with the toxicity of metal powders, the causes of lung damage. These are things that you need to be aware of as you're talking to your safety team. It's very helpful if you understand them and can work with them to build procedures around those types of hazards. The breathing tests that are very useful if you need to, if you're trying to decide whether or not to use respirators, some other PPE that's appropriate, how to clean air filters safely, the atmospheric filters in the laser powder bed, good cleaning practice in general, and some of the tools that you can use. And with that, that closes our slides. I will stop sharing my screen. Just one moment. All right, and with that, I will close. I guess at this point we will.
Yeah, perfect. Thank you, Emma and Amy. What a great presentation. We'll now get started with the Q&A portion. As a reminder, we'll attempt to answer as many of the questions that have been submitted. We've got a lot of great questions here. So authors of the questions that do not get answered during this live broadcast, you will get emailed with the answers in the coming days. So let's just jump right in. First, we have a two-part question. Can pycnometer density be used as an indicator of powder internal porosity given APS tomography might not be available? And are those pores vacuum or filled with atomizing gas?
I can speak to that. So I should, yes, have mentioned pycnometry as a density measurement according to ASTM B923-02, which was updated in 2008. It's a standard test method for metal powder skeletal density by helium or nitrogen pycnometry. There's also MPIF standard 63, which is the method for determination of density for MIM components using a gas pycnometer. So those are both resources that could be pulled to looking at density. But again, pycnometry is a volume measurement. It's not an actual density measurement. So you're getting your total volume of the powder divided by your separately measured weight, and then you have to incorporate those together for your total number, which then gives you some error and perhaps won't give you as much information in that 2 to 4% range where you might be sitting for your powder, and how those might change. It might not be sensitive enough, so you can kind of take that with a grain of salt. Yeah, and then what was the second part of the question?
Sure. Are those pores vacuumed or filled with atomizing gas?
Oh, yes. Okay, so the common understanding at this moment is that those pores have trapped atomization gas, so typically argon or nitrogen, and so that even that gas bubble stays within the melt pool within the AM process and then stays within the part. So then even though you're hipping perhaps or hot isostatic pressing the part afterwards, you're just compressing that gas bubble and making it smaller, but you're not actually eliminating that porosity even using the HIP process. So that's the common understanding for the most part, is that it's a trapped gas bubble pore, not just an empty vacuum.
Okay, great. Was composition taken with the Auger electrons as a function of depth?
Yes, those profiles that I showed in my slides were taken as a function of depth. And with Auger electron spectroscopy, you do have to be careful that you have a standard that you're measuring and correlating for your measurement and for your measurement depth profile, because you're just basically turning on the argon ion beam for a certain amount of time, and so you have to be able to correlate that to a standard for your particular material and know that that's how deep you're going as you're etching away the surface. And so yes, those profiles were a function of depth.
Okay, great. I have another Auger electron question. It's another two-parter here. Can Auger electron spectroscopy be used for a 3D printed part? And then the second part of that was, how does this technique compare to energy dispersive X-ray spectroscopy?
Yes, Auger can be used for a bulk material and for a 3D printed part. And it is the difference there between Auger and EDS is the depth sensitivity. Actually, Auger electrons are a lower energy levels, so they are typically confined to the very surface of the powder or the part, or the surface that you're looking at. So that's how you can get such nice depth profiling and measurements of those electron signals as you're going through the material. When you're looking at EDS measurements, those are your energy dispersive X-rays, and those are coming up to a micron, from within a micron, or up even, I mean, depending upon your beam parameters, perhaps even deeper than that from within the sample. So that's not going to be as sensitive to the surface. Again, when those profiles that I was showing you were down under 10 nanometers in depth of where that oxide surface is. So you need to be using the measurement technique that's going to give you the data that you want. And so, yes, while both Auger and EDS give you composition information, the spatial distribution from where that composition information is coming is completely different.
Okay, great. And then we also had a comment, and Amy, I don't know if you have any more that you want to add on to this, but you had mentioned the issue of extinguishing metal fires with water, but it should be mentioned that some metal powders, for example, aluminum, are dangerous when wet, even at room temperature. So you mentioned flooding paper filters with water to inert them. This comment was he assumed that those paper filters aren't rated for aluminum. So he just wanted to make sure that for guidance, it's not misconstrued as a recommendation to flood all filtered materials with water. Do you have anything you could add on to that, Amy?
Yeah, sure. So yeah, we don't use water to extinguish, but we can use water to react the surface of a powder. So for like aluminum in like a wet vacuum, it actually does move through the water to form that oxide layer, which is then stable. So I guess you could see it as kind of a stabilizing thing. And I'm actually not aware of the difference for like an aluminum filter, air filter, and a laser powder bed. But yeah, that is definitely something to consider. Depending on the material you're using, you will need to look at your procedure for handling those filters and see if it's appropriate. So yeah, that's a good point. Just yeah, we could just take the procedure that we developed as an example of what you might need to do to swap your filters out safely.